Welcome to qnawire.
Here, we have defined the velocities for two different satellites orbiting the Earth at different radii. So, if we consider a satellite, we know that a satellite is really just falling around the Earth as the Earth moves away from it. And that motion is circular. So, some force must be creating some kind of centripetal force to keep the satellite moving in that motion. And the only force that could possibly be causing that is gravity, pulling the satellite closer to the Earth. Now, the equation for the gravitational force is, let me write somewhere where you can see the whole thing. Fg is m1 times m2 times capital G, which is the gravitational constant, all over r squared. So that's the distance between our two objects. All right, so if that's what's causing the gravitational force, then we know that we can equate these two. Now, in this case, our first mass, m1, is going to be just the mass of the satellite itself. Our second mass is going to be the mass of the Earth, which we're going to label me, since that's the other object that is attracting the satellite to it. And the distance between them is still just r squared. Now, we can cancel out the mass of the satellite and rearrange to get that v must be equal to the gravitational constant times the mass of the Earth divided by r. Now, we have to be careful when we consider r, because let's draw a picture of the satellite moving around Earth. If our satellite is this little red X here, then we have the distance between the satellite and the Earth itself. That is our RA or RB, depending on which part of the problem we're working on. And we have the distance from the surface of the Earth all the way to the center, the radius of the Earth itself. So that means that r is equal to RA or RB, remember that's a slash to indicate one or the other, not a division sign, plus the radius of the Earth itself. And knowing that, we can solve our problem. So let's solve for satellite A first. We know that VA is equal to G times the mass of the Earth over RA plus RE. And now we can plug in our quantities. The gravitational constant is just a number that you can memorize or get on an equation sheet, depending. And that's probably equal to that looks like a multiplication sign. Let me get rid of that. 6.67 times 10 to the negative 11, and it's in units of newtons, meters squared, kilograms, times the mass of the Earth, which is equal to 5.98 times 10 to the 24 kilograms. And that's just a number that you can look up and is also given in the textbook. And all of that is divided by our total radius, which is 3.6 times 10 to the 5th meters, which is our given radius, RA, but in meters, plus the radius of the Earth, which is 6.38 times 10 to the 6th meters. And that's also a quantity that's given in your textbook. When we plug into this, we find that the velocity of our first satellite, satellite A, is 7.693 times 10 cubed meters per second. Now to look at satellite B. I think, then the units for gravitational constant should have kilograms squared up here, not just kilograms. All right, on to satellite B. So really just the same concept, we're just plugging in different numbers. We use the same equation, G, the mass of the Earth, over RB plus RE, and when we plug in, we get the same thing. The only difference is our radius, 6.67 times 10 to the negative 11 newtons meters squared over kilograms squared, times 5.98 times 10 to the 24 kilograms, our mass of the Earth, and all over our given radius, in meters, not kilometers, plus our Earth's radius. And that is going to give us a velocity of 7.495 times 10 cubed meters per second. And that's the answer to our second part of the problem.